Welcome to CodeUp's Data Scientist Day. My name is Jason Strawn. I'm the co-founder and CEO of CodeUp. To kick off this Data Scientist Day, I would like to give you a formal introduction to CodeUp. Thank you.
Thanks, Jason. Hi, my name is Dimitri, and I'm the VP of Placement with CodeUp. CodeUp is a 22-week full-time career accelerator that trains data scientists across the entire data science pipeline, then places them at companies like USAA, HEB, Booz Allen Hamilton, EY, Accenture Federal Services, and Gaphy Analytics. If you're looking for someone to dive into your company's data, look no further than our data science grads. With experience in statistical analysis, machine learning models, Python, SQL, Tableau, and much more, they're ready to add value across your organization from day one. In the capstone project you're about to see, they worked in teams as full-time data scientists to deliver actionable insights. To kick off our presentations, here's Team 311.
What's the 311? Well, to put it simply, 311 is a non-emergency number to report things such as potholes, stray animals, trash collection, or other city requests. Now, although these calls are labeled as non-emergency, they are still essential to keeping our city clean and safe. So how would your calls be handled based on your situation? But before we delve into this, I would like to introduce to you the team that you will be hearing from today. My name is Caitlin Carney, and after I share the highlights and overview, Gabby Broussard will be taking you through acquiring, preparing, as well as initial exploration. Sam Keeler and Lori Segovia will be sharing our key takeaways from exploration, and then John Grinstead will be sharing our modeling process before I see you again for the conclusion of this insightful tale. We also hope you enjoy a tour of the murals of San Antonio used throughout this presentation. To start, we needed to know what we wanted to accomplish. Ask ourselves if there was a link between location, department, reporting time, and the speed in which a case was being completed. Our goal was to find the main drivers of response times and use these to create a model to predict a case's level of response. We also aimed to see how each feature affects the level of delay. We found that department, season, and the number of days given for resolution were major drivers of response time, and that district was a driver, but only when working in conjunction with the department or reason for calling. We have multiple recommendations, which we will be covering more in the conclusion, but our primary recommendation is to reassess each department and their cases in order to create a standardized case timeline based on the department and reason for calling. But before I end up giving too much away, I'm going to be handing this off to Gabby, who will be taking you through the next steps of your journey.
Thank you, Caitlin. We began with acquiring. We obtained our main data from the City of San Antonio open data sets. We chose the 311 department logs because we want to ensure that everyone throughout San Antonio has an equitable opportunity for having their case solved on time. We also got supplemental data regarding the demographics of each district from the San Antonio 2020 website. We chose this website as a data source because the Department of Planning and Community Development published the site as a summary report of the demographic distributions of San Antonio using the U.S. Census Bureau results. You might be wondering, why did we choose this topic? Imagine there's an aggressive loose dog on your street and you're unable to leave your house without being attacked. You call 311 and they say they will come pick up the dog, but hours turn into days and the dog is still there. So you start to wonder, is timeliness an issue on a departmental level, or is this a larger issue only affecting my side of town? To prepare our data, we merged some data variables to prevent misclassification and made case status a Boolean variable. We also made new features and created the target variable, which is level of delay. The level of delay measures if a case is resolved very early, on time, late, or very late. This was done through bending the comparison of the number of days used to the number of days allotted for a case to be completed. We handled the null values and dropped any duplicated or unnecessary variables. We then changed feature names to be easier to understand. One of the last steps we took of preparation was to split the data using sklearn into the train, validate, and test data sets. Then for modeling, we dropped our object column, scaled the numeric data using the sklearn min-max scaler, and split the data into XY datasets. The next step in the pipeline we used was explore. There are 10 districts in San Antonio. Districts 1 and 5, along with a small portion of 7, make up the urban core. District 2 and a portion of 10 make up the east side. District 6 and a portion of 7 make up the west side. Districts 3 and 4 make up the south side of San Antonio. The rest of District 7 and 10, along with all of District 8 and 9, make up the north side. Some findings from exploring our districts are that Districts 1 through 5 have a higher amount of reports, Districts 8 and 9 have far fewer early responses, and we attribute this to them having fewer calls compared to all the other districts. The departments for the City of San Antonio are Solid Waste Management, Development Services, Animal Care Services, Transit Capital Improvements, Customer Service, Metro Health, Code Enforcement, and Parks and Rec. The department with the most calls is the Solid Waste Management Department, which handles all trash-related calls. The departments with the least amount of calls are Parks and Rec, Customer Service, and Metro Health. Key findings from exploring departments were that each department has certain cases and areas where they perform well, but then their timeliness drops in other areas. The department with the most issues with the level of delay is the Customer Service Department. I'm now going to pass the next stage of exploration to Sam.
Thanks, Gabby. First thing I want to do is dive deeper into the departments. You won't find Parks and Recreation on these charts though, as they only made up 3 calls of our whole data frame. On the top graph showing average calls per day, we can see that the departments that are most frequently called on are Waste Management, Development Services, and Animal Care Services. Now looking at response times by department on the bottom, you'll notice that our frequently called departments tend to get the job done on time. But as we get into the less frequently called departments, they begin to have some issues, most notably Customer Service and Code Enforcement, which we had first-hand experience with, as we have emailed Customer Service throughout the course of this project and have yet to hear a reply. The next thing we're going to talk about is how the seasonality affects 311 calls. As you can see from the top graph, when we get into our fall and winter months, call volume tends to drop. We think that this may be a result of the weather itself, as in the colder months, people are less likely to be out reporting things to 311. Now, if you look at the bottom graph, you'll see the response time by the month. One would think that with a lower call volume, response time may improve, as resources and time can be allotted to the smaller number of cases being brought up. However, when we looked into response times during these so-called slow months, we found that response times actually got worse as the call volume fell. In the months of October through March, there was a 10-day difference in the mean response time when compared to April through September. Next, we're going to look at proportion of calls by department and how seasonality affects them. You'll notice that Animal Care Services Department has a large increase in percent of calls during the winter months. We hypothesize that this is because people may be leaving their pets out in the cold, resulting in more animal neglect calls which Animal Services would have to respond to. We also notice that Development Services has an increase in percent of calls during the summer months, probably a result of people being out and about, causing more wear and tear on the city, as well as more people being out to report things to 311. Now I'm going to hand things off to Lori, who will talk about the different regions of San Antonio.
Thanks, Sam. Let's explore the different regions of San Antonio to see how they differ across the city. Before we look at each region, let's take a look at the overall proportion of level of responses to service calls in San Antonio. In this data set, only 12% of the cases fall in late category, and 88% of the cases fall into an on-time or early category. With this in mind, let's look at the regions. The East region is comprised of Council Districts 2 and 10 and represents about 21% of our data. This region has the slowest response time, with an average response time across all service calls of 4 days. Moving on to the next region, we have the South region, which is comprised of Council Districts 3 and 4, representing 23% of our data. When we compared the average response time between South and East regions, we found no significant difference, but significant difference in the average response time was observed between West, North, and Central regions. The West region is comprised of Council Districts 6 and 7 and makes up 18% of our data. As you can see, the average response time for this region doubles when compared to the previous regions, although the amount of service calls received is less. This difference in average response time was found to not occur by chance when compared to South, East, and Central regions. The North region is comprised of Council Districts 8 and 9 and represents 11% of our data. This region has the least amount of late responses and the greatest amount of early responses. Council Districts 1 and 5 make up the Central region, which is the smallest in area that makes up the biggest proportion of our data, holding 27% of the service calls received. This region has the highest level of very early responses. The average response time for this region is 14 days, which means that this region, on average, completed the service requested 14 days ahead of the due date. 2 weeks ahead of the scheduled due date might make it seem like the city is working super fast, but upon investigation, many cases are given generous amounts of time to be completed, when that time might not be necessary. For example, the average time allotted to resolve an illegally parked oversized car in this region is 132 days, when it typically only takes 5 days to complete. Overall, many of the region's average response times were found to be significantly different when compared across other regions. So what does that tell us? That the region of the service call plays a role in how quickly that issue was responded to. Let's now predict the level of response with John in modeling.
Thank you, Lori, for that introduction. So once we had concluded our exploration and found the features we believed to be significant, we then proceeded to modeling to see if we could create a machine learning model that could accurately predict whether a case would be resolved early, late, very late, or on time. Before we could proceed into modeling, however, we first had to establish a baseline prediction, as this would be our goal to make a machine learning model that could outperform a baseline. We found our baseline by exploring our target variable, the response times. It was discovered that of all cases in our data frame, 57% of cases were resolved very early, which means that if you assumed every 311 case that the city of San Antonio handled would be resolved very early, you would be correct about a little over half of the time. While this is great news for the city of San Antonio, it provided a lofty goal for us to reach in order to beat our baseline. In our modeling stage, we had utilized multiple machine learning algorithms and recorded their performance for comparison. On our training data, we found that the best performing models were the decision tree and the random forest models, each capable of improving upon the baseline by approximately 8 to 10%. Ultimately, we proceeded with the decision tree model as it had performed slightly better on unseen validate data than the random forest, which had a slight dip in performance. We also found that our decision tree model had the highest recall and precision for both early and late cases, which is very important for minimizing errors when setting expectations for resolution time. Overall, the decision tree had a consistent performance on training and unseen data, making it our most valuable model. While we are pleased with this model's performance, we do plan to improve upon this with future iterations. And with that, I would now like to welcome back Caitlin, who will share with you our conclusion.
Thank you, John. So in conclusion, we found that each department has better levels in certain locations than they do in others, with the exception of customer service, which is universally late. Each case type is resolved with different speeds based on the region, but the number of days given is also very different between these areas. And finally, winter months tend to have the longest average number of days open, and autumn months the shortest. With more time, we would like to further evaluate the time it takes to resolve cases between locations, create a feature for priority level, and we would also like to obtain census data to gain insights to locations and the demographics beyond just districts. Before we come to an end, we would like to recommend to review and create standardized case timelines for each department. More specifically, all late cases should be investigated further to see if we can find the causes of latency issues in departments. And finally, we recommend that the classification of the current data set for late or not late be recreated. This feature labels cases that were completed on time as late cases. Here's the appendix where you can find a link to our GitHub repository where you can learn more about what we learned. And you can also find further information on features used for this project, as well as a link to an interactive map pinpointing the murals in San Antonio, which we used to design this presentation. We hope you enjoyed our tale of San Antonio, and we would like to extend thank you from our team to yours.
As you just saw, the capstones are an end-to-end data science project. The teams start by identifying a problem in dataset, forming a hypothesis, and determining stakeholders. Then they wrangle real, messy data to analyze, model, and visualize in order to form actionable insights. Finally, they deliver their key takeaways and recommendations in these presentations. They work on this entirely remotely as full-time data scientists, utilizing Zoom for daily Scrum meetings and virtual Kanban boards. With our next capstone presentation, here's Team America's Blue.
Hello, Amanda Gomez here with Team MG² to welcome you to our project, America's Blues, an analysis of fatal police encounters. At MG², we strive to make the world a better place. Our capstone project has tasked us with identifying key attributes that lead to fatal police encounters. Initial hypotheses have been tested to find recommendations to help save lives on both sides. Let's meet Team MG². We have Matthew Dalton, Alicia Gonzalez, Barbara Marcus, and myself, Amanda Gomez. On our agenda today is our executive summary, a discussion of our analysis process, attributes uncovered from our data set, and model performance. We'll wrap up with steps to put our recommendations into motion, and additional in-depth analysis is located in the appendix. Our project's overarching goal is to analyze available data from our fatal police encounters, to build a model predicting the civilian's threat status in order to create possible recommendations to save lives on both sides of the aisle. Some of the most impactful features in determining victim threat status were if the civilian was unarmed, whether they were allegedly in possession of a firearm, if they were attempting to flee the police, their age, and race. Our classification model outperformed baseline by 20%. Recommendations we'd like to see implemented are national standardized documentation, mandatory surveillance, specialized social workers, and allocation of healthcare funds. I will walk you through our process and allow our data to set the stage for our story today. We began setting the framework of our project by gathering our data and determining our target attribute as threat level. Threat level was determined by the researchers as the victim being armed or in attacking mode at the time of death. Using a Trello board, we created and assigned tasks to reach our final product. We acquired our data from Mapping Police Violence and FatalEncounters.org, then diligently cleaned and prepared our data for exploration of features against our target and performed statistical tests to gain insight into creating the best model for predicting the threat level of the victim that we present to you today. Now, the big picture process may seem linear, but don't let that fool you. There were many twists and turns that forged a pathway that looked much more like an obstacle course that Matthew will recap for you now.
Thank you very much, Amanda. As Amanda stated earlier, we acquired our data from mappingpoliceviolence.org, where they provided a complete dataset to download and use. This dataset was compiled of 3 different sources: Fatal Encounters Database, the FBI National Use of Force Database, and the Washington Post Police Shooting Database. This dataset contained over 9,000 recorded fatalities from January 2013 to May 2021. Unfortunately, after data preparation, only 69% of this dataset was usable, leaving us with just over 6,200 records, which we felt like was insufficient amount of data to provide a fair analysis. So we searched for additional records to add to our current dataset. Fortunately, Fatal Encounters had a database that solved this issue. This dataset was created and maintained by paid researchers that painstakingly pull public records and cross-verify crowdsourced information. Incredibly, this dataset contained encounters dating back to January 2000, extending our data 13 years and increasing the number of records to just over 30,000. Even though only 44% of these records were usable, we still gained more than double of the total number of usable records from the previous data set. So now that we have our data, I will explain how we wrangled this data for analytics. We began by importing our raw spreadsheet data into DeepNote, a browser-based real-time collaborative notebook, and using Python, we converted this data into a pandas data frame and familiarized ourselves with the features and values. We dropped the victim's name for anonymity, statistically useless columns that contain links to images and news articles, and columns that simply contain too many null values. We use NumPy in conjunction with pandas to group similar values with specific columns like alleged weapon and fleeing, not fleeing. And finally, we created dummy variables that hold a binary value that indicate the presence or absence of a feature. Here's an example directly from our wrangle. As you can see, we began with our raw data. Then we lowercased all text and replaced the white space with underscores. And then by using NumPy and pandas, we were able to group like values. In this example, handguns and rifles alike are grouped simply as firearm. During our wrangle, we ran into a lot of challenges. I'm going to highlight the 4 most significant challenges we faced. The biggest hurdle we needed to overcome before objectively looking at our data was to remove bias. With a sensitive topic like this, it is easy to be swayed by emotions. So at every step of the pipeline, we reviewed our results and made sure the data had a voice and was speaking for itself. Non-standardized reporting caused a significant issue during our wrangle because there are so many phrases that are synonymous with each other. One example, the terms traffic stop, traffic violation, and pulled over. They're all essentially the same scenario that could have initiated an encounter. Grouping values like these was paramount in creating our data set for exploration and modeling. Additionally, it is almost impossible to discern what actually was going on during these fatal encounters because there was just a lack of details within the descriptions. This forced us to drop the majority of our null values instead of using statistical methods to adequately fill them in. And finally, as stated earlier, the small data set. Initially, our data set was just over 9,000 records. Fortunately, we were able to remedy this issue by using the Fatal Encounters dataset with over 30,000 records. And now I'll pass it over to Alicia, who will go over the exploration process.
Thank you, Matthew. So to reiterate, we are analyzing the attributes that surround fatal incidents during these police encounters and seeing how they stack up against a victim's threat status, meaning that they are attacking police or putting others in harm's way. The whole purpose of our discoveries is to help our goal of saving lives, providing insights, and finding recommendations to improve the safety and outcomes for all people involved, both officers and civilians. We start assessing a victim's threat level by asking key questions regarding the victim's armed status, fleeing status, whether there is a known or unknown mental illness for the victim, and how do these influence threat level. Also, we want to figure out how do body cameras and gender impact threat level, and how does mental illness appear across each gender. Let's take a look. As expected, armed victims are at a high threat level with 74%. Of course it's high. They are armed with some type of weapon and putting officers or other people in danger. This may be why these incidents result in fatal outcomes. But then we have 69% of victims that are unarmed and not considered a threat. This is a high percentage as well. And something to think about when coming up with solutions is how can we avoid these fatal incidents with the non-threatening unarmed victims? Now, in regards to victims' fleeing status, non-fleeing victims have a higher probability of being threats. This could be due to civilians fighting back or attacking law enforcement, while on the other hand, some fleeing victims are considered threatening, possibly because they are creating a hazard to others. Nonetheless, fleeing victims do have a slight higher probability of not being threats. For mental illness, whether the victim is known to have one or not, all instances have been more likely to be threatening. We find it interesting, though, that the highest percentage of threats appear to be the victims identified as not having a mental illness. So why are they distinguished as threats? If they tended to their mental health, would they be attacking police officers? Maybe then this percentage would go down. Now, victims with a mental illness, could threatening events be lessened if there were co-response teams or mental health professionals mitigating the scene of the crisis? Again, things to think about in order to decrease fatal outcomes. Now, how do body cameras make a difference in alleged threat level? When body cameras are on, there is a higher chance of a non-threat level than if they are off. As you see here, there is a 5% difference. In addition, we see that there is a higher chance of a threat when the body cameras are off. It's a small difference, but there is a better chance of having non-threatening situations when body cameras are on. Therefore, it would be better for all involved to have body cameras be mandatory across the board. With gender, males have the highest threat level and females trail closely behind. It is almost equally likely for both to have a threatening status. So how does a victim's mental illness appear across each gender? Well, males are more often categorized as not having a mental illness than females. However, they have a high threat level according to the previous visual, and both genders have higher percentages of known mental illness. Could this be related to limited mental health awareness and support across the country? So to sum it all up, let's go over possible improvements to be made from our data analysis. Let's try to avoid fatalities on unarmed victims, be wary of fleeing and non-fleeing victims, keep body cameras on, have mental health support teams work in conjunction with law enforcement, and create more mental health awareness overall. We hope these discoveries provide assistance in assessing a victim's threat level and finding solutions to address the fatal encounters between police and civilians. Now I will hand it off to Barbara to go into modeling.
Thank you, Alicia. We took the insights we gained from our exploration and began to build models. First, we used two feature selection algorithms, Select K-Best and Recursive Feature Elimination, to rank all of our features in order of importance. The result was a list of 11 features that would be most impactful for predicting threat level. Combined, these features described whether or not the victim was fleeing, whether or not the victim was armed, as well as the race and the age of the victim. Next, we established a baseline prediction. To do this, we compared the occurrences of our 3 threat levels: threat, no threat, and ambiguous threat. Since threat was our most common outcome, we predicted each occurrence as a threat. Our baseline predictions were accurate 52% of the time. Now we needed to create a model that would use the selected features to classify the threat level of each incident. Using Python's scikit-learn library, we tested 4 different classification models: decision tree, random forest, k-nearest neighbor, and logistic regression on our selected features to see which would best predict the outcome. Although all 4 of our models beat baseline, our best performing model was a decision tree, which correctly classified threat level nearly 72% of the time. Here's a simplified example of how our classification model works. The model begins by asking a question, such as, was the victim armed? If true, it takes the left path, grouping that instance with others that were also armed. And then a second question, did the victim have a firearm, is applied to further split the group. Otherwise, the observation is grouped to the right, and another question, was the victim fleeing, is applied to further divide that data. This process continues iteratively until it reaches a maximum preset depth. Our model had a maximum depth of 3. At that point, a prediction is generated to classify groups based on the target class that has the most instances. Finally, we applied our decision tree model to out-of-sample data using the 11 selected combination features, our 3 classes, and a maximum tree depth of 3. Using our decision tree model, we correctly classified threat level nearly 72% of the time. This is compared to our baseline accuracy of 52%, so our end result represents a percent of change in accuracy of 39%. Now that we've looked at all the steps in our data science pipeline, here's Amanda to summarize our findings and recommendations.
Thanks, Barbara. Now to wrap up. Our classification model's accuracy increased by 20 percentage points, equating to a rate of improvement of almost 40%. The most impactful features found were whether the victim was armed, if they were attempting to flee, their age, and race. We recommend a standardized documentation system for fatal encounters that immediately syncs with the FBI database that is currently voluntary to report to. We'd also like to support the documentation with mandatory body or dashboard cameras, Using specialized workers to respond to cases of mental crises can also help alleviate police. And an allocation of funds to increase the availability of healthcare to the community in efforts of decreasing the number of mental welfare check calls to 911. Given a dataset that includes non-fatal observations, America's Blues can be extended to create a classification model to predict if an encounter would end fatally and the features to minimize that chance. And lastly, to set our recommendations into play, make your voice heard by contacting your local and state representatives. New Jersey Senator Booker is currently laying out the framework of police reform legislation that includes collecting accurate data. So vote on issues you care about. Please feel free to peruse our appendix, repository, website for more visuals at your leisure. And on behalf of Team MG², thank you for your time and attention.
Here at CodeUp, we don't just teach technical skills like stats, SQL, Python, and various other tools. We also teach our students how to learn and approach new problems with perseverance and self-reliance. This is what builds adaptable professionals. They can learn to use whatever tools they have to create meaningful solutions. This adaptive expertise is often referred to as learning agility, one of the most highly sought after qualities in the tech field. As you watch our next presentation, you'll see how this group turned a problem into an innovative solution. Here's Team Off the Rails.
Hello, and welcome to Off the Rails. Did you know that railways account for 1/3 of U.S. exports? And in just the last 8 years alone, they have suffered over $2 billion worth of damages due to railway accidents? Our team set out to find which railways, under which conditions, were most likely to be involved in accidents. I'm Steve Kane, and our team is thrilled to have the opportunity to share our presentation with you today. First, I'd like to introduce you to the talented team of data scientists at OTR Analytics that have collaborated on this project. I should take a moment here to note that while our team is dividing up this presentation, each of us has gone through the data science pipeline and thoroughly analyzed these data sets. Besides myself, our team consists of Gabriella Tiorina, Justin Sullivan, and David Birchelman. Now on to the agenda. First, I'll go over a bird's eye view of the details. Then I'll dive into our data acquisition, and Gabriella will describe our data preparation. Then we'll take you deeper into the analysis of our two data sets. Justin will cover equipment rail accidents, while David will handle highway rail accidents. Then I'll wrap it all up with our insights and final thoughts. Our team set out with the goal of building a machine learning model to analyze which railway would be involved in an accident. The data showed few discernible differences between railway companies when it comes to accidents solely involving equipment. In the cases of accidents involving motorists or pedestrians, however, some differences did come to light. The data appeared to show that some railroads tend to have accidents in recurring locations, usually areas involving the general public. This led us to suspect that human error is likely at fault. Our recommendation is that local government, as well as the industry itself, take a closer look at these trouble spots. Let's move on to the process. We planned our project step by step using Trello, and we acquired our data from the Federal Railroad Administration's website. We prepared our datasets using Pandas and NumPy and explored with Matplotlib, Seaborn, and NLTK. We employed classification models such as logistic regression and random forest, and to deliver this presentation to you, we used Tableau. For this project, we poured over 8 years worth of data from the Federal Railroad Administration's public database to find the drivers of railway accidents. We obtained CSVs from 2 different datasets containing over 23,000 observations, gathered from 2012 to 2020. We were faced immediately with a dilemma. Do we keep the datasets separate or do we merge them? Ultimately, while these sets did share some common features, they represented 2 different types of incidents, and we made the decision to keep them separate. Now Gabriella will explain how we explored our data.
Thank you, Steve. So where do the railroads in our analysis operate? One of the first things we discovered is that these railroad companies operate in different regions across the United States. For our analysis, we used railroad companies as our target to gain a deep understanding of the relationships between railroad companies and other features that play a role in railroad accidents. I will now tell you about how we prepared our data for our analysis. Our data structure consists of 2 data frames, one for highway rail accidents and one for rail equipment accidents. For data preparation for both equipment and highway rail accidents, We dropped columns with 80% of null values, removed unnecessary features, and removed columns with duplicate information. In addition, we dropped observations where railroad companies had less than 300 accidents and engineered 2 new features, one for season and one for region. Each observation included an accident report, so we used natural language processing to extract and analyze information from those reports. There are 2 types of features used in our analysis: input features and output features. Input features are those that can affect railroad company accidents at any given time, such as weather, season, railcar count, and location. Output features are a direct result of the accident that occurred. These output features, death, damages, injuries, and reports, provide the most amount of analysis and information for a railroad company. This chart shows representation of railroads in sample by accident class. Our dataset is imbalanced, with Union Pacific having more observations than any other railroad company, and we dealt with imbalances by stratifying our data by railroad when splitting the data into train, validate, and test. Next, Justin will go into our analysis of equipment rail accidents.
Thank you, Gabriella. We'll now talk about our findings and analysis for equipment rail accidents. What defines an equipment rail accident? That's an accident resulting from the failure, either mechanical or physical, of the train itself or the track on which it travels. We'll now talk about some of the features that play into an equipment rail accident. As Gabriella mentioned, there's 2 types: the input features, such as train speed, location, number of rail cars. There's also the output features, or the outcomes of the accident itself, such as total damages, number of people injured, or even number of people killed. Through our analysis, 2 of these features in particular arose to the top: train speed and total damages. Let's now take a look at these features individually and see how they impacted our classification model's performance. We'll start with total damages. We asked ourselves, is there a difference in total damages by railroad? We hypothesized that if there was, we might be able to explore that further to determine if one railroad was being more negligent in the way they operate, and that was resulting in more total damages. A quick visualization like this box and whisker plot seemed to imply to us that yes, there does seem to be a difference in total damages by railroad. This was further confirmed with statistical testing, where we ran a Mann-Whitney U-test due to the fact that total damages was not normally distributed. That further confirmed that there is a statistical difference between total damages by railroad. So we carry this over as a feature. How did our classification model perform with total damages? Well, our random forest classifier was our best performing model on out-of-sample data, achieving a 42% overall accuracy in predicting railroad. However, this is really only 4 percentage points better than our baseline accuracy model. Further evaluation of our model's performance by looking at the F1 scores, the harmonic mean between precision and recall, showed us that really our model was only good at predicting Union Pacific Railroad. So we went back to our data and we looked at additional features such as train speed. We asked, is there a difference in train speed by railroad at the time of these accidents? With a quick visualization and some statistical testing, we were able to determine yes, there is a difference in that fact that Amtrak does travel at higher speeds than any of the other railroads. This makes sense to us given the fact that Amtrak is typically carrying passengers while the other 4 railroads in our study are carrying heavy freight. Still, we decided to utilize train speed and total damages and retrain our classification model. With both of those features input, we did see improvement in our random forest classifier model. However, all of that improvement could be attributed to the fact that the model was now able to better classify Amtrak railroads. We saw no improvement in classifying any of the other railroads. So what are our takeaways? While total damages was able to predict Union Pacific Railroad and train speed helped predict Amtrak Railroad, no features or combination of features used to train our classification models to predict which railroad would be involved in an equipment accident ever did so consistently. This, in and of itself, is a takeaway. We determined that there's no one railroad that is operating with any more or less negligence than any other railroad. However, because these railroads still do have an impact, both financially and sometimes cost human lives, it's important that railroads continue to monitor these accidents, perhaps bringing in additional data, such as equipment maintenance schedules, and also looking at high-risk routes or locations where these accidents are likely to occur. Further, through our exploration of the accident reports themselves using natural language processing, one of the most frequent phrases that came up in all of these accident reports was leakage of hazardous materials. This certainly has an environmental impact, and we suggest that railroads continue to monitor this environmental impact and include it in their reporting on these accidents. I'll now pass this off to David, who will share with us our findings on highway rail accidents. David?
Thank you, Justin. So what is a highway rail accident? It's an accident that involves a train and a pedestrian, or a train and a motor vehicle. So every week for the last 8 years, rail companies have been involved in accidents that have accounted for over 6 deaths, 19 injuries, and over $329,000 in damages. With this in mind, one of the first questions that arose was, are rail accidents related to the season of the year? Well, to verify this, I ran a chi-square test, and the result was that we were not able to reject the null hypothesis that rail accidents are independent of season. So the next question we delved into was a relationship in damages by season. The thought was that volatile weather conditions in winter and spring may lead to higher damages for rail companies. Again, after doing further statistical testing, this one with the Mann-Whitney U-test, it was found that this was not the case either. For example, in 2012, winter had the highest damages, while in 2014, winter had the least amount. While the amount of damages do vary based on the railroad involved, there was not a seasonality to the frequency of incidents occurring, nor a seasonality to the damages incurred. In fact, most accidents took place on clear days with zero obstruction, so there isn't a special set of weather conditions required for an accident to take place. So what features will we take into our modeling to determine if we can predict what rail company was involved in an accident? Well, out of over 50 possible features, it was found through exploration that monetary damages and railcar quantity would be the most effective in addition to the location where the accident occurred. As you can see with this dual axis graph, having the highest median quantity of railcars doesn't necessarily equate to a higher median damage amount. For example, BNSF has a high railcar quantity, but a low damage amount, while CSX on the other hand has a high railcar quantity and a high damage amount. Now this would be looked at further, but first we wanted to run our model and see how well our features did. As mentioned previously, we focused on classification model that and ultimately settled on random forest as it was our best performing. Now with a baseline accuracy of 25%, our model was able to improve up to 60% accuracy after adding in damages and railcar quantity, which was a 140% increase. Now seeing such a jump in accuracy on our test data, let us want to explore the relationship between the length of trains and the damages incurred. Was there a possibility of a linear relationship between the two variables? Could rail companies predict possible damages based on the length of trains they were sending out? Well, a quick scatter plot answered that question with a resounding no. There was no linear relationship between train length and damage amount. So what does this tell us? Well, it tells us that there must be an outside factor at play. The good news is there doesn't appear to be one striking feature that differentiates one company from another. The biggest factor at play is the one element that railroads can't control, and that's the decision making of those operating the motor vehicles or those walking across the tracks. So where does this take us? Well, we found that the majority of those motorists involved in a highway rail accident were 25 to 60-year-old males. We also determined that there were some rail crossings that saw upwards of 16 incidents at the same crossing over the last 8 years. So while we are not able to go that deep during this round of exploration, we believe it could be advantageous to overlay the latest Census Bureau data and determine where the largest population density clusters of males reside, and then determine their proximity to all active rail crossings. Now, another recommendation that we have is that we'd also like to know the frequency of train trips through each crossing so it can be determined how likely an accident is to take place. Now, with this information, rail companies, insurance companies, and government entities can enact awareness campaigns to try and reduce the number of deadly and costly accidents, while also determining if new and enhanced safety guidelines are needed at crossings that have seen multiple incidents. Like one single rail crossing in Gary, Louisiana, a town of just 2,700 people, that has seen 6 incidents over 8 years that has resulted in 5 deaths and over $44,000 in damages. Steve, back to you.
Thank you, David. The data sets that we viewed indicated that, for the most part, railroads are consistent as far as accidents solely involving equipment are concerned. However, when you add in the human element, they quickly become unpredictable. One way to mitigate this would be for local governments and the industry itself to take a keener interest in these preventable tragedies. I'd like to invite you to visit our GitHub page to take a look at our Jupyter Notebook, as well as a deeper dive into our data sets. On behalf of the rest of the team at OTR Analytics, I'd like to thank you for your time and attention, and to remind you to travel safely.
In our program, we don't rely solely on lecture, theory, and hypotheticals. Instead, we put our students to work with raw data sets of all shapes and sizes, exposing students to ambiguity, outliers, and imbalanced data. We use real, messy data sets so that students are prepared to clean and analyze whatever information they're given on the job. While many programs rely on theoretical knowledge and pre-cleaned data sets, our students have worked hands-on throughout the entire data science pipeline: planning, acquisition, preparation, exploration, modeling, and delivery. As you watch this next group, pay special attention to how they acquired and prepared their data. Here's Team Fake News.
Hello everyone, my name is Liam Jackson. My team and I will be presenting an in-depth analysis on the detection of fake news articles through the use of machine learning. Through this project, we hope to add perspective, reduce noise, and educate the general public on the information they receive, while also acting as a counterweight for other fact-checking organizations. We are excited to be here and present our findings to you today. So let's get started. Throughout our presentation, we will introduce the team, explain our goals and key takeaways through our executive summary, explain the intricate project pipeline, walk through acquire, preparation, exploration, and modeling. We will also introduce the launch of our web application called the Fake News Detector. And finally, we will share our conclusions, recommendations, and our team's next steps. Our team consists of David Aviola, who will be presenting the project pipeline and the acquire and preparation that was done to the data. Brennan Bryant will present our data exploration. Ken Alviola will present the modeling and the web application. And I will be presenting the executive summary, while also wrapping up the presentation with a conclusion, some recommendations, and our team's next steps. The problem we are trying to solve is that each year more and more individuals are becoming victims of misinformation online. Our team's goal is to create a classification model that can accurately identify and predict fake news articles across the web. We will accomplish this in a data-driven fashion through the use of Natural Language Toolkit, Scikit-learn, and other data science libraries. Through extensive experimentation, our team determined that a logistic regression model performed the best at 98% accuracy. This model was 78% more accurate at predicting fake news articles than our baseline result. Through hypothesis testing, we determined that the fake news articles are significantly more subjective than real news. We also found that there was no significant variation of polarity between the means of fake news and real news articles. Be sure to pay close attention to the words subjectivity and polarity. We will be discussing the meaning of these measurements in more detail throughout our presentation. In addition to our machine learning model, our team developed a web application, which we will also talk a little bit more about throughout the presentation. Now I'd like to dive a little bit deeper into the problem behind fake news. As the amount of consumers of web-based information skyrocket each year, the threat of misleading information and fake news becomes more imminent. According to a study by the Pew Research Center, close to 38% of US adults prefer acquiring their information and news from online sources. Our team believes that with our fake news detector, the public is better equipped and protected from false information when scouring the internet. Let's look at a few examples of titles. Can you spot the fake title? Our first title, Trump's chief strategist Steve Bannon compares himself to Darth Vader and Satan. Our second title, Explosion outside Athens court shatters windows, no injuries. Now these were pretty obvious. Now let's look at another example. Can you spot the fake titles in this one? Our first title, Russian military, US coalition predator drones spotted at time and place of Syria UN aid convoy attack. Our second title, McMaster says, of course Trump supports NATO Article 5. These two titles were not so obvious to identify, so now we have to explore the article text to determine if it is classified as real or fake. Now David will talk about the steps we took to do that.
Thanks, Liam. We followed the data science pipeline where we first acquired our data and then made it ready to explore in the preparation phase using Pandas, NumPy, and Jupyter Notebook. During exploration, we used tools like Seaborn, Matplotlib, NLTK, and Spacey to identify characteristics that could be beneficial during modeling. We then statistically tested the hypotheses that we came up with during planning. Finally, we established our baseline and evaluated 5 different classification models from the scikit-learn library before settling on the best one according to our priorities. We were able to incorporate the best model into a web application using the Streamlit library. Also, since the work is never done, we laid out the tasks we want accomplished, either by us or the open source community, to expand this project. Now that you have an idea of our process, let's go into further detail for each phase. We acquired the data from Kaggle in its raw state. One file containing nearly 21,500 real news articles from Reuters, and the other containing nearly 23,500 fake news articles from websites which were flagged by PolitiFact as unreliable. Each of these articles had a headline, text body, subject, and were published between 2015 and 2018. Since the data was not ready for exploration, we first had to prepare it. Even though the data was split into fake news and real news files, we still had to label it with an isFake column where the fake news observations had a value of true. With the data labeled, we were able to combine the 2 files into a single data frame. Next, we decided to standardize the date format and then converted the column into a Pandas datetime object to perform time series analysis on a future iteration. We also discovered about 600 observations were missing text, and another 5,700 articles had duplicate headlines and text bodies. These data points were removed. We then moved into the natural language processing, or the NLP pipeline. For both headlines and text, we removed special characters, lowercased all the text, tokenized the text to create discrete units, lemmatized the text in order to retain only a dictionary form of a word, and removed stop words like is, a, and the. Using the Spacey library, we were able to perform sentiment analysis for each article's headline and text body by calculating polarity and subjectivity scores. The resulting data frame had a shape of nearly 39,000 rows and 11 columns. This data frame was split into 3 samples. 55% was reserved to train the models, 25% to validate our initial models for overfitting, and 20% to test the final model on unseen data. To help you better understand sentiment analysis, I'll explain what the different measurements mean. Polarity scores range from -1 to 1 and indicated how positive or negative the words in a headline or text body were. For example, the positive headline, China says has made best effort on North Korea ahead of Trump visit, received a score of 1, while a negative headline like Bernie Sanders shoots Hillary the evil eye during Dem debate was scored -1. Subjectivity scores range from 0 to 1, where a score closer to 0 indicated mostly objective statements, and a score closer to 1 were mostly opinion. An objective statement like Obama discusses Islamic State threat with Pentagon chief has a score of 0, and there's something really creepy about Melania Trump's signature received a score of 1. With these measurements, we are finally ready for exploration. Let's hear from Brandon about our findings.
Thanks, David. After acquiring and preparing the data, the next step in our pipeline was exploration. During this step, we took a deep dive into the data to identify any interesting findings utilizing bigrams, trigrams, word clouds, as well as a bit of statistical testing to get a better grasp as to how to approach modeling, the next phase in our pipeline. We started by examining the counts and ratios of words in all the articles and found that some of the top for real news were said, Trump, US, and state. Some of the top words for fake news articles were Trump, people, president, and one. Across all news articles, some of the top words were the same. However, there are certain words such as time, Donald, people, and Clinton that appeared in greater proportion throughout the fake news stories. We found that fake news articles tended to have words with negative connotations such as bigoted, insane, and idiot. And real news articles use words that are more centered around world events and places. We explored further by analyzing the frequencies of bigrams, which are 2 consecutive words in a sentence, and found that some of the top for real news were United States, Donald Trump, and North Korea. Some of the top bigrams for fake news were Donald Trump, image via, and Hillary Clinton. We then moved on to trigrams, which are 3 consecutive words in a sentence, and found that some of the top for real news were President Donald Trump, President Barack Obama, and White House said. Some of the top trigrams for fake news were J. Trump at Real Donald Trump, New York Times, and Black Lives Matter. In analyzing frequencies of fake news words, we saw that the word Trump was the top word prevalent across all fake news articles, with over 52% of all the articles that contained the word being considered fake news. Another interesting find was the large amount of Twitter usernames present in the text body of fake news. Over 24,000 Twitter usernames total were found in fake news articles, as opposed to 800 in real news articles over the entirety of our dataset. We then moved on to hypothesis testing to find if the text polarity of fake news articles was more negative than that of real news articles, and were unable to find any significant difference between mean polarities. We also asked if the mean text subjectivity of fake news was greater than real news, and found that fake news in fact scored a 22% higher mean than real news subjectivity. This helped us understand a bit more about our sentiment analysis, also known as opinion mining. We were able to visualize the questions asked during hypothesis testing, such as there being little to no difference in mean text polarity, and that the mean text subjectivity of fake news articles was in fact 22% higher than the text subjectivity of real news articles. Lastly, using k-means clustering, we were able to create sentiment clusters based on the subjectivity and polarity scores of the text. The 6 different clusters generated were negative bias but mostly factual, negative bias and non-factual, positive bias but mostly factual, positive bias and non-factual, unbiased and factual, and unbiased but mostly non-factual. Also, we were able to find that as text subjectivity goes up, text becomes more polarized in all directions. After deciphering these interesting characteristics in our data, the team felt we had enough to move on to modeling, the next phase of our pipeline. Ken will now take you through that process.
Thank you, Brandon. Now I'll give a quick overview of our modeling process. First, we take the clean text from our NLP pipeline and assign each token a numerical value by calculating term frequency times the inverse document frequency using a process called TF-IDF vectorization. Term frequency being the number of times the word appears in an article, and inverse document frequency being the inverse of the number of articles the word appears in. Then we feed the vectorized text into our machine learning classifier to make predictions on whether an article is fake or not. After building multiple classifiers, we decided on a logistic regression model because it had the highest overall accuracy of 98% on out-of-sample data. We started with a baseline accuracy of 55%, and we were able to make a 78% improvement, resulting in approximately 3,300 more correct predictions on unseen data. Now, we acknowledge that typically we don't see accuracies this high on test data, and we're skeptical ourselves, but we took steps to ensure our data was split correctly, make sure our model was fit only on training data set, and validated and tested on 2 out-of-sample data sets. We also verified on Kaggle that other teams were achieving similar results. Here's a short explanation on how the model works. The vectorized tokens, meaning the text from an article body, are combined linearly using their coefficient values assigned by the model to predict the probability of a true or false prediction. In our case, fake is the positive class and real is the negative. Here are the top drivers for each class according to our model, ranked by their coefficients. For real predictions, the word said has the largest negative coefficient, indicating that a lot of real quotes can be found in the text body. The next most influential words towards a real prediction are the location of Washington and days of the week, such as Wednesday, Tuesday, Thursday, indicating the structure of real news usually has dates and locations. For fake predictions, our model's top words are image and via, suggesting fake news outsources a lot of images in their articles. Names of political figures also rank high towards fake predictions, reflecting on the political climate from 2015 to 2018. And another interesting find is that GOP, the nickname of the Republican Party, is found more often in fake predictions than the full name, but although not pictured here, the opposite is true for real predictions. Next, we integrate our logistic model into a web app using the Streamlit library in Python. This app takes a body of text or an article URL, runs it through our NLP pipeline, and feeds it to our model to output a fake or real prediction, as well as the probabilities for each case. The app then creates a simple word cloud, uses the Spacey library to calculate polarity and subjectivity ratings, and performs named entity recognition. Although this app is still in the early testing phase, I encourage everyone to visit easleyfakenewsdetector.com or scan the QR code at the end of this presentation to test the app yourself. Now, I'll hand it off to Liam to close out this presentation.
Thanks, Ken. Throughout this project, our team was able to identify the key words and phrases associated with fake and real news articles through the use of bigrams, trigrams, and word frequency charts. Through statistical testing, we discovered that there was little to no significant variance in text polarization. But when it came to subjectivity, fake news articles were 22% more subjective in nature than real news articles. Our team is confident that we have a highly accurate model backed by statistical tests and proven real-world implementation. At 98% accuracy, we believe our model can help bring balance to the internet while achieving our ultimate goal of reducing the number of occurrences of people falling victim to fake news online. We recommend using our application in conjunction with other research, knowing that there could be a possibility of bias depending on the data that is assigned to our model. We also recommend cloning our repo and diving deeper with deep learning models and neural networks. In the future, our team would like to look at using the cluster names as new labels to increase the accuracy among new data and features. We also would like to conduct time series analysis on the polarity and subjectivity scores using the dates and time given through the dataset. If you would like to learn more information about the data we collected, our research and analysis, we invite you to use the links below to access the original data source from Kaggle, our GitHub repo, and our fake news detector web application. That concludes our presentation. On behalf of the entire team, we thank you for listening and have a great day.
And there you have it. That concludes today's capstone presentations. Thank you to everybody for joining us to see the impressive work our data science graduates put in. If you're an employer that's already ready to hire a data scientist trained in the most in-demand skills, head over to alumni.codeup.com. You can find resumes, contact information, LinkedIn profiles, and more so that you can get the candidates you're looking for. Or you can contact us at partners@codeup.com and we'll hand select a few candidates just for you. Family and friends, please stick around so you can watch our students reminisce on some of their favorite CodeUp memories and thank their supporters. A private Zoom celebration link will follow these videos. Thank you to everybody and have a fantastic day.